thank you for everybody who showed up again. I promise, I think next week you have somebody else, so you don't have to hear me going on and pontificating about fallacies and such. Anyway, so let's continue. I mean, today what I'll talk about is not so much, these are not really fallacies. I've shown you two big fallacies that would really qualify as fallacies last time, but today I'm just going to talk about some points that are easily sort of missed. Even I myself have sometimes made simple errors in reasoning, not so much widespread fallacies. And let's just let me see whether I can somehow, I can't move my screen. Oh yeah, it's a little bit of a delay. So the real fallacies I talked about were these two up here. So I'm not gonna go back to them again. Then what we'll talk about today is we're gonna finish the double dipping or overfitting discussion, which was a little rushed last time. I've shown you a few examples, but then I didn't really talk about remedies. But then today we'll talk about some things that are not so much fallacies, but things that are good to keep in mind. First of all, differences in the strength of the association of two variables. It's important which one are you considering, slope or correlation. All of these come out of autobiographical experiences that I have. This one was once a discussion with a very high prominent psychology professor. I'm not going to mention her name, but she asked me, can you look at this difference in the strength of association? And I asked her which one, the slope or the correlation. And she was kind of befuddled by the question and got almost sort of upset with me. And I said, look, those are two different things and they could have different implications. And so I thought it would be good to clarify this. Then this is an easy one, model adjustment. Does it mean that your predictions are now orthogonal to any confounders? We're going to talk about this. This is very easy to make this, in other words, to make this assumption when it's not true. And I myself have made the mistake. Some people in my division, particularly, this is often relevant when age is a confounder for some things that have experiential value. In this particular case, it was a postdoc. I think I can't remember where she's now, but she had a very interesting set of issues where she wanted to look at an outcome that was dependent on age, but also financial experience, when making everyday life financial literacy decisions, which sometimes are compromised in aging. And she found, the interesting thing is that the one regressor is very confounded with age, yet when I run a model, I still get independent contributions above and beyond age, but my partial model is still collinear with age. How can that be? And I'm just going to show you that this is very easy to appreciate, but it's easy to forget. And then the last one, this is maybe possibly a little overstated. Again, this is my Chris Habeck's personal issue that has maybe happened more at Columbia than other places, where often variance is used as if it was an absolute statistic, like a p-value or something, and people make sort of intuitive gut level judgments about variance. And I'm just saying, you should just keep in mind what variance is and what it isn't. So, and hopefully we'll cover all of this. I put the variance fallacy at the end. If we don't get through that isn't the biggest problem. We could easily miss that. There's some other things here. I'm cut them out. I think a lot of this. So let's get going. So last time, these were the things that I covered. My favorite is the Gaussian variable fallacy. Do dependent or independent variables have to be normally distributed? Otherwise, OLS linear regression is not correct. I try to convince you, no, that is wrong, although it's often assumed. You can safely debunk this. And people also ask, how do I counter this? When reviewers bring this up, and I'd like to point out, and I can share this maybe later with Benedetta, there are three papers. There's my colleague Adam Brickman and we wrote a note This isn't really peer reviewed because we got so frustrated. This was submitted a few times. And basically we got a response by the editor often saying, oh, what are you talking about? Nobody would commit this fallacy. I think you're complaining about a red herring. This fallacy doesn't exist. So we got frustrated, ran out of steam, and just posted it on bioRxiv. But there are some peer-reviewed published accounts that talk about this fallacy. So you can, the next time somebody harps someone about your variables not looking non-normal, you can just quote these two papers. Then the other one was a favorite of mine, transitivity of correlations. Does a correlation between variables A and B and C, does it imply that A and C are also correlated? Sorry, this should be a comma, not a smaller sign. And also here the answer is no. So, and I showed some poignant example that was constructed where, you have two variables, there was a diet variable with neuroinflammation, AFB, and neuroinflammation and cognition. And you might be tempted to think that, oh, diet therefore is obviously correlated with cognition, but I showed an example where I constructed it such that it wasn't, and it's very easy to pick up a counterexample. So also here, be careful if you have pairwise relationships between variables, then it's very hard to reason about an unobserved pairwise relationship that's outstanding. So that was pretty simple. Then we started to talk about anti-Occam, overfitting, and what's called double dipping. All of these are different names for the same thing. And I showed you a few examples that I thought were quite poignant. They were somewhat contrived because they were so outrageous. And then we fell short of the remedies. Here's again the general resource page, which I could also share later. I mean, there are a lot of accounts, this is very selective. I found these quite enjoyable, but probably since then there are many, many more accounts. Sort of the Dutch tradition, I think maybe in collaboration or around E.J. Wagenmarker's, there's a real sort of strong tendency of inferential hygiene where people will really go and check papers, and sometimes this is a little confrontational, but I think it should all be constructive. If people make mistakes, then one should help them along. And see, these are just some book accounts that also sort of cast doubt a little bit on frequentist inference in general, and then sometimes develops into this very sort of it's a more a performative ritual, that doesn't really tell you a whole lot if done badly, right? So, okay, what are the reasons for double dipping? I think that we can recall them again, maybe, neuroimaging in my field is very complex with complex pre-processing pipelines where each stage sort of occupies careers of a whole bunch of people, right? I mean, so it's very easy to get something that is not only not robust, but possibly introduces artifacts that later show up, Then I talked about the difficulty of exact repetition of analytic recipes, here, I think also in Europe, but in the United States, there's a lot of attention paid to that. Provenance is clearly documented. Ideally, you can download whole data objects that have data sets, software versions you're using. And for any paper, that's what ultimately should be the endpoint. And then one could say systemic and cultural reasons. I mean, data exploration is important, but seeming rigor is also highly prized. So what people often did is they really explored the data, but then pretended that this was a confirmation of an a priori hypothesis, and we might all be guilty to some extent. So this is probably done. This is done mostly by honest researchers who make small, there's small nudges pushing you one way. It's probably much less outright fraud, I would say, although, there are few cases of outright fraud, but, there's pressure for publication on career success, and replication really until recently wasn't highly prized, right? It doesn't give you, just to replicate a study, it's not going to land you a very high profile paper, although it's arguably quite important. Also, important is to publish null results, and there are also journals now where the paper gets submitted, it gets accepted on the strength of the analysis plan and the data acquisition, and then the result will be published no matter what, even if it's a null result. Okay. So what are examples of double dipping? Many things I gave, but I showed an example where you peek at the data and repeatedly run statistical tests, and your null distribution now becomes wider and the tails become fatter. And everybody's possibly guilty of this a little bit, seeing where the data analysis leads you, or you're doing something that's ad hoc but highly iterative. And you convince yourself, oh, but this really was the recipe that I wanted to undertake in the beginning. And it wasn't fixed in advance, but in my mind, I write the introduction section as if this was the plan, So this is easy to fall prey to, and we all have done it to some extent, I would say. And that's what some people have called, I think Andrew Gelman calls it harking, hypothesizing after results are known, harking. So in real world scenarios, just to have this schematic here, imagine you have different analytic stages. It could be pre-processing, or you do something to the data. And very often you do your formal inference on the last stage. But ideally you should, do the inference on the whole chain of pre-processing. This is sometimes extremely complicated for neuroimaging, right? But ideally, you should commute the data or create null conditions and then consider everything, and that will get you the real null distribution you're testing against. And well, that's hard to do, but here are some safeguards, and I'm not the only one. There are now many published accounts. Write down. The biggest one I think is write down your analytic recipe before embarking on any data analysis. This doesn't have to be hard coded. This could be an if-then condition. You could have decision trees in there, but it should be all nailed down so that you can execute this whole analytic recipe on null data with permutation or Monte Carlo tests for realistic p values. Another one is if you have data, if you can replicate an out of sample, if you have some data that you can set aside, then that's very, very valuable, because however smart you think you are, the best thing is just to try it in data. This is an honest test. And just for overall sort of epistemic hygiene, data exploration is good and necessary. I definitely do not want to trash data exploration. Exploratory sometimes has a very pejorative feel, but exploration is important. Just mark it very clearly where you do data exploration. Don't dress it up as confirmation just because you want to appear inferentially rigorous, right? And here's some examples what you can easily do. I showed it. First of all, I want to show you how things go wrong, or not go wrong, but how things change when you do something unwittingly. But also, if you write down your recipe beforehand, you can do this on real data and get the adequate p level. So for instance, this is really highly contrived. Imagine you have two samples, x and y. You sample them from a normal distribution. They're not really correlated. This is a null scenario. We compute the correlation, and we do this many times. And you can see the blue. We do this 1,000 times. You see the blue curve. That's our distribution. It's centered on 0. It looks about as you would expect it. There's some little jaggedy edges because of sampling variability. Now imagine we do something, now when we have the 50 values, we check all, we do a leave one out procedure, or what's called a jackknife, and leave out, one at a time, and compute the correlation of the residual 49, and then we just pick the maximum value of that. So we strategically leave one observation out just to get a higher correlation. So if you do that, you see, first of all, you're as you expect, all of a sudden you're slightly biased. The tails are getting, I think, a little wider, but you're mainly biased. Now you're not centered on 0 anymore. So you did something to your distribution, and even null data now where before you might have judged something as not significant, now you might judge it as significant, right? This is another really, really easy example. Imagine you sampling male height. Imagine there's a country called Aborigania, right? And the average male is 178 centimeters tall. And this is really the distribution that it looks like, you know, I mean, and now imagine you sampling, again, you sample 100 people 1,000 times and you compute the sample means. But again, you do something to the sampling. First of all, here, this is the one-shot procedure where you take all 100 in your sample. And you see the violin plot shows a nice, you're centered over 178, so that makes sense. But now imagine you just leave out the worst, sorry, there's no value judgment, leave out the smallest, you know, or the shortest male in that sample, right? And what you get, you can see there's a slight creeping up. So even leaving 1 out of 99 will give you a slight bias. But then if you leave out the 10 shortest, I should really have, that's very bad. It's not worst, it's shortest. After you leave out the 10 shortest people, you can see there's a substantial bias now, right? And you can see the interquartile ranges are not touching anymore, they're not overlapping. So this again is rather obvious. You're doing something to your data that invalidates a test, right? If you now were to run a one sample t-test or comparison to 178 centimeters, here you will get something highly significant. But what you did is really, you didn't do something kosher because you sampled and then did something selectively to the data you had, right? It's just in real scenario, it's not so obvious to diagnose probably what you did, but this just gives you a flavor. You know, you're doing something to the data that invalidates your statistical inference. But if you write down beforehand your analytic recipe, then you can execute this on also null data and really can check, do I have p-value inflation or not? Okay, so this is the most important double dipping safeguard, I think. You know, write down the recipe, analyze, you know, do it on null data. And so this is quite easy to do. I think this is a good exercise in general to think what constitutes good replication or successful replication. Is it brain behavioral relationships with the same sign? Is it something more? In a brain data set, is it the same regions showing up? So this is already a very good exercise to do. So don't make stuff up on the fly. I'm a little whimsical. I said what doesn't work for movie script also doesn't work for analysis script. Okay, and now let's, there's one more thing, the file draw problem of publication bias. That's kind of a similar thing. I mean, because it just happens at a higher level that as a field, you know, if null results have a very hard time to get published, then any, you know, the official record of a finding will be distorted, and people doing meta-analysis will now get overestimates, right? Because they're averaging over results that are artificially of higher effect size than they otherwise would be, right? So it's a kind of double dipping. Last time I gave this example of the stock newsletter fraud, which was similar, where only the participants of a correct prediction got an offer for signing up. And this is similar to the file draw problem. And again, it's a very simple didactic simulation. Imagine you have this normal distribution, you know, it's centered on 50, has also a standard deviation, population standard deviation of 50. Let's sample with repeating sample sizes that can vary, right? And here I get the logarithm of the sample size, so we can vary from 10 to all the way to 10,000. This is the decadic logarithm. And you see what normally should happen, this is something sort of funnel plot. There's also this might be different quantities that this might also be the standard deviation, or the variability on the estimate you get might be plotted here. But what normally it looks like something like this, and it makes sense that the more data you have, the closer to the true population result get, right? You can see that once you at 100, at an n of 100, you have this sort of width, at 10, you have this. And so slowly you converge, to the right value from both sides. You should approach from below and above, and that's why it's called a funnel, so this is usually what this would look like. But if you have any kind of sampling publication bias in there, imagine now, just for real, this is a very simple reason. Imagine I did a one sample t-test, and I only sort of allowed values that have at least a p-value of less than 0.01 in my one sample t-test. Then you see those red dots, they would be censored, they would be missing from my publication record. So therefore, if I now did some averaging to come up with a population estimate, this would be spectacularly wrong, right? And there are tools, I'm not going to talk about these tools. From the funnel plot itself, you can assess whether there is publication bias, and there's a whole inferential calculus with that. We're not going to talk about that, but this is just to tell you, publication bias is another kind of double dipping, or it's something, by omission bias, right? Okay, so this would be a good time to stop if somebody has any questions. I'm sorry, I don't know why my screen keeps hanging, but it seems to be working now.
Yes, now we have time for discussion.
Or any more questions? I tried last time, I also tried to show an algorithmic. So in other words, you can fit overly complex models, or you do something, where you say, imagine you compare old and young on one variable. Oh, you don't find anything. You pick another variable and you keep going. So all of these things, they're not ideal. You're probably inflating the p value. So your nominal p value at the end of that process will be too small, right? And this also, I tried to last time explain, it's also, this is also algorithmically. Imagine you're doing a lot of things to the data. You're not fitting an over complex model. You're just doing many iterative steps. They're not sufficiently nailed down. Then also you might get p-value inflation. So your nominal p-value might appear lower than it actually is. Okay, so if there's no more question, let me just, we're moving at a fairly slow pace. Let's see that we can make tracks. So this one, again, it's not a fallacy, it's more a clarification that's maybe helpful. So adjusting for a confounder ensures orthogonality of partial prediction. That's quite a mouthful jargon term. That's the fallacy, by the way. If you believe that, like for instance, for many years thought that was assured, that's wrong. And let me show you why. So imagine standard adjustments for nuisance covariates, and it doesn't matter whether you have a design matrix. This could be one explanatory variable, or it could be many. It doesn't really matter, but for simplicity, assume we have one here. But so what we do, I do this almost every day, right? And imagine we're interested in the relation between y and x, but adjusted for confounder c, right? There's some or more variables that are sort of nuisance variables. And very often in our science, we do not have a statistical control and a strong control like a random clinical trial, right? So we have things that are confounded. And so very often we'll put in these nuisance variables, run the regression, and you might find, for instance, here you have a brain measure, here you have, say, a cognitive measure in there, and here you have age, right? And you know often that age and cognition are confounded. So you're interested at the association between cognition and, say, cortical thickness. That's an example I will show, above and beyond age, right? So you can run a general linear model, and you might get significant results. What's interesting, or what's easy to miss, is that the partial model of X and Y, that the partial model X is still as collinear as X and C are. And this is mathematically trivial to see, but it's not fully appreciated. I'm going to show you some examples, right? So imagine here, this was a while ago, we had 386 people. We have a measure of verbal intelligence called the NART IQ, or I think it's North American Adult Reading Test. We have the years of education and age, and I computed the mean cortical thickness coming out of the free surfer. You get two hemispheres, you average them. And now you see these are all quite collinear. NART, in our sample, we have a lifespan sample. We try to randomly recruit people, but often we find that older people are more motivated, better educated, and they also happen to be smarter verbally than the younger folks. Despite our best efforts, you see there's some residual correlation, right? And now the common analysis rationale would be, let us control for all these variables and put them into the regression simultaneously, right? We have mean thickness, we have our intelligence variable, we have education, we have age, intercept, and we have some unaccounted for residual. And we see we're getting some results, and we see that the strong relationship between the mean cortical thickness and NART, as well as age, but there's no education. So these are linear regression results. So we can say, there's a strong relation between NART and thickness above and beyond age, right? However, if you look at the partial model now, if you just take the part in thickness explained by NART, you might, and this has happened to me and has happened to other people, when you correlate it with age, you still find that there's a strong correlation with age and education there, right? Even though the contribution to thickness is above and beyond age and education. You can see from earlier, the correlation is exactly the same, and that's the mathematically trivial aspect to appreciate once you think about it a little bit. The correlation between X and Y, when you have an affine transformation where you multiply X by a slope parameter and you add an intercept, that correlation will be exactly the same. It doesn't matter whether you shift things up and down or change the slope, right? But that's exactly what we do just in the partial model, right? It's just a linear affine formula. So this is, this came, I have to say, several years ago, this came surprising initially, but then I thought about it and was like, yeah, this is always the case, right? If you have a linear affine model, it will always show the exact same collinearity as between the original covariates, right? So one thing you could, what's the remedy for this? And in particular in the case where age is correlated with, like in this colleague's example where age was correlated with experience, and you really wanted to tease out how much experience contributed to an outcome above and beyond age. First of all, you could do obviously partial correlations, right? You could residualize both thickness and the NART variable with respect to age and education. That's easy to do, and many software packages will do it already automatically. You compute the bivariate correlation between the residuals, and you get a result. Well, at least in MATLAB, if you do the partial correlation, the p-value is just ascertained from the last step. Ideally, again, you would have to get an accurate estimate, you would have to do this whole two-step procedure, many times on null data. Most often, probably the p-value is the same, but most rigorously, that wouldn't be enough just to take the last step. It's also a conceptual drawback. What you're doing now is highly derivative. You are really correlating residuals to one another, right? And some people might find that it's a once removed judgment, right? You're really not looking at the first order quantities anymore. You're just having, it's always residualized with respect to these other covariates. So they become very important, right? So one thing you could do, another thing you could do, although it's not ideal, is you could subsample the data and you can impose orthogonality, right? You could take some subsample of the data and make it such that NART education and age are independent of one another, have no more correlations. So there's no more confounding, right? The drawbacks are, first of all, you're doing it only for a subsample of the data, wasting data, right? Because you can't impose orthogonality on the full sample because the things are confounded, right? So you have to waste data, and you now have dependence on hyperparameters. How big is your subsample that you're using, right? Or what's the stringency of the orthogonality? Are you saying the correlation should have a p-value bigger than 0.05, bigger than 0.2, bigger than 0.5? So this isn't ideal either, although it's conceptually nice, but it is maybe really inferentially rigorous. The inferential rigor becomes dependent on these hyperparameters, right? And just to show you what happens if you do this, imagine you have now we have 386, and let's pick 80, that's a subsample, and let's assume the orthogonality is, so the correlation amongst these variables should be less, have a p-value of higher than 0.05. And you can see when you do this, and you run the linear regression, and you look at the t-value of the relationship between NART and thickness, you see that most of the time you get a significant prediction, right? You have more than 95% of the time there's a positive value, right? But when you make the orthogonality more stringent, if I make this threshold higher, I can only achieve this with a lower data set, and all of a sudden here now, this doesn't look so good anymore. Only in 88% of the subsampling distribution do we find a correlation between NART and thickness. So this is just to show you, I'm not really advocating that you do this, but just to show you, that this is quite a significant problem. Really, my punchline is that there's really no good way out to have statistical control. You can't pretend everything else being equal because things weren't equal. And there's some ways you can deal with this, but it's good to keep in mind what you're doing and what you can't achieve. So the random clinical trials where you really impose orthogonality by your sampling, by your recruitment, right? You make sure that people only differ in the one parameter that you're interested in. They obviously remain superior. There's no way we can do these statistical sleight of hands, but they might not be as strong as we think, right? And also the one side point is that there should be, what I often encounter, and I have made this mistake myself, there should be better awareness of the differences between partial correlations and confounder adjustment in a regression. The two are not the same, right? Because there could be this collinearity still when you run models with collinear confounders, whereas partial correlations, that really imposes orthogonality. So it's much more stringent. Okay, so that's somewhat an arcane point. I hope you just keep in mind that first, it's good, you can run models this way. I run models this way almost every day, right? But it's good to keep in mind, a contribution of X to Y, can be there above and beyond confounders, but that partial model that accounts, that X accounts for Y could still be quite collinear to the covariate or the confounder, just to keep that in mind, right? Okay, the next one is a little easier. If there's any, okay, I'll move on. We can also talk about it later. This one will be a little easier to appreciate, I think, than the one before. So starting from this, again, this autobiographical recall of this conversation that I had with this colleague who she's a very big, in particular neuropsychology, and the frustration that she had to appreciate the difference between slope and correlation. I'm just going to show some example here. Just most people, when you think about it, again, it's not that difficult to appreciate. But so differences in the strength of the association between slope and correlation. So this only comes into play when you are comparing something, right? When you just have a one sample test, then the two are totally identical, really. If we again look at this data set I had before here, I took mean cortical thickness and I had a different intelligence measure of fluid reasoning, and I varied the sample size just to get some variation on here. If you look at the model prediction of a linear regression where you have the slope parameter versus a correlation between the two variables, thickness and fluid reasoning, then you see that there's a perfectly monotonic and there's almost an identity line here, right? So that it is an identity line, right? There's really no difference, the strength of the association, or particularly the inferential judgment about the association of two variables in one sample, doesn't matter whether you do a normal bivariate correlation or you write this as a linear regression. It doesn't matter, you'll get the same answer here, as you can see. Now the real fun starts when you have a comparison, either between two samples where you look at the same variables, or if you have two outcomes in the same sample. Then you'll start to possibly run into some, not problems, but you need to be sure what you're doing. So let's first recall some elementary facts. So first of all, slope is not a dimensionless quantity. A slope usually has the exact dimensions that you have, and actually I made a mistake here, it's unit y divided by the unit of x, right? And I always joke with my colleagues that they're really sick of this joke that psychology is a very weirdly dimensionless discipline. You hardly ever deal with dimensions, although dimensional analysis sometimes can tell you something important, right? So slope is not dimensionless. If you have accuracy, regressed against reaction time, your slope will be % correct per millisecond or second, right? That will be the unit. Whereas correlation is dimensionless, right? Because you're really relating two things that have somehow been, you somehow have accounted for the dimensions, and it just measures the tightness of the x to y relationship, regardless of slope. And that can, so this is in a comparison, these two could be quite different. They could be the same, they don't have to be. That's the answer. So let's imagine the first scenario, we just have one sample with independent variable x, and we have two dependent variables, y1 and y2. And they have possibly different units, right? In this case, a test of the difference in slope seems somewhat meaningless already to begin with, because you're really comparing apples to oranges. It probably, in a case such as this, probably the test of the difference in correlations, and these are dependent correlations because it's the same sample. And there's a test for that. Steiger's test is a parametric test you can use. That's probably more appropriate, right? So imagine you have, again, thickness in the same people, mean cortical thickness, but you have two cognitive outcomes, right? You have one neuropsychological test where, say a fluency test where it's the number of items somebody can recall in a fixed time period versus the accuracy on the decision test. So these are different units, and you're now interested in, what's the difference in correlation? Does thickness account better for the fluency measure versus the accuracy measure, right? If you thought about a test of slope, it seems very weird already because this is already how the slope has different units, so it's kind of a bit strange, right? So it would be much more much more appropriate to have a difference in correlation here. Let's go to the second scenario. This is maybe more important, where you have two samples with independent variable X and dependent variable Y. So it's the same variables, but now two different samples. And, and they're parametric tests, again, of the difference in correlation or the difference in slope for those. But now the slope and the correlation difference can be probed, and they might behave differently from another. And I'm going to give you a very contrived example where they behave in the opposite way. But let's first look at the scenario one. And the lines got lost. I had like lines here, but here there's a difference in I constructed the data red and black such that this is totally, again, mock data. It's a simulation that I cooked up. So you see the slope is actually the same. I made it the same, but you can see that the black dots have much less tightness around this average line that would look like something like this. And here, I said there's parametric tests, but let's do, I just did a bootstrap, because that's easy to do and I'm lazy. And so let's first of all, bootstrap, let's sample with replacement for both samples and just look at the correlation difference, red minus black, when we do that. You can see here that the probability of a difference is more than 99.4%. So there's obviously a difference in correlation, but now we do the same bootstrap test for the slope difference, and you can see, no, there really isn't, right? If I generate all these bootstrap samples, subtract the slope and plot the difference, you see that's almost nicely centered around 0, but it's definitely not one way of 0, one way, either way of 0. There's nothing, so the slopes are not different. So you can imagine I could now do the opposite. I could make the slopes different, but the correlation the same. And my inferential test, whether you do it bootstrapping or you do the parametric tests that are available in most software packages, you might find a similar disjunction. So I'm not going to do this because it's so obvious. But imagine I now do this interesting thing. This might not happen very often in real data. I now made the slope in the black higher, but I made the tightness is pretty poor of these dots around the black line, whereas the slope in the red is lower, but it's pretty tight around there. So I've constructed a difference in slope and an opposite difference in correlation, right? So if we do this test now, you see there's a difference in correlation. The red has a much better correlation than the black, but the black has a much bigger slope. So if we just compare red minus black, we're on the left side of 0, right? So this is, as I said, somewhat contrived. Maybe this never happens, but you have to think about what this really means and what you want to compare. Are you interested in the slope? Really tells you for 1 unit change in X, you get a particular change in Y. Is that what you're interested in? Because you're really interested in some kind of model parameter. We talked about the Sternberg last time, the amount of time per item maybe that you use. Is that really what you're interested in? Or is it just the correlation, the fact that you can predict Y from X with much better tightness in the red, although the slope is actually lower, right? So you have to really, again, I don't have any answer. You have to think exactly what you want to do in this strength of association difference test. And that's what I said also to my colleague, with whom I had this somewhat frustrating sort of talk. She thought I was just going to be difficult rather than helping her. I kept pointing out these nuances, and she couldn't see why that was important. But I'm saying maybe it's good to think about this a little bit, the implications. How often this happens in real life? Probably not very much. It's probably quite I've concocted this, with mock data, but this could happen, right? The two could behave in opposite ways, and you have to think about what you're really interested in. Okay. We have a few minutes left. I'm not sure. Yeah, we will not get very far, although the message here also is not very difficult. I don't know, should we press on or should I stop here for some more discussion? You guys.
Well, we have 5 minutes, I would say. So either you can cover the variance fetishism in 3 minutes, and then we keep 2 minutes for discussion.
Yeah, we can. To be honest, I can, even if I don't get through all the slides. It's in a way, it's just a very easy point. So again, this might be more my issue. You might say, oh, this is all trivial, but what I've noticed sometimes is that the way people talk about variances can be somewhat misleading, and people will talk about this as if it is an inferential statistic. So you might hear that there's consternation when something accounts only for 2%, in the outcome, whereas 10% might be more acceptable. But people have often very gut level judgments. And I'm just pointing out that variance is a descriptive statistic. It depends on the tightness of the association and the sample size, right? It's not an absolute standalone statistic. And let's just do this one thing here. Imagine this is a very simple Monte Carlo simulation where you regress X against Y and you introduce varying levels of noise and you have varying numbers of observations. You can see this, the variance accounted for in the dependent variable to the P level. And you can see there's not a tight relationship at all, right? It's just a cloud of points. And imagine you get a curve only when you fix the number of observations, right? So to talk about variance with floating numbers of observations is already quite misleading. It makes sense. It made sense, for instance, in neuroimaging at a time when you had low sample sizes, and you had sample sizes less than 50. I remember imaging studies with n equals 10, n equals 6, n equals 20 was quite nice. In that case, there's probably a reasonable good tight relationship between variance and P level, but if you have much bigger data sets, n equals 1,000, then this becomes kind of meaningless talk, right? The same happens not only for the variance accounted for in outcome, but also if you look for variance accounted in the imaging data itself. For instance, here we have 3,480 task activation maps. These are people, from a study at Columbia called the Referenceability Neural Network Study, where, we have 290 people doing 12 tasks. So if you throw all of this into a PCA, then you see the first principal component accounts for 8% of the variance. And, once you go far out, principal component 3,000 will account for much, much less than 1%. So any linear combination of these has, by definition, has to have less variance in the data than PC1 and more than PCN. And what I have found very often, you can come up with patterns that account for 1% of the variance, yet are highly reproducible and really correlate with important functional or demographic variables also out of sample, right? So all of this is to say variance is a descriptive statistic, it's not an absolute statistic. And also the point that we made last time, if you don't pay attention to model complexity, then optimizing the variance can lead to overfitting, right? That's actually the corollary here. So variance by itself, isn't very useful because it's dependent on n and the tightness of the relationship, the effect size, or the P level. It was a good, useful heuristic in a time of consistently small data sets, but today I would say it isn't super useful anymore. Particularly in epidemiological data set, I don't think people ask for variance accounted for that much. You could have very, very small variances accounted for that are highly, highly significant. That's the nature of multi-causal, high-dimensional, and very rich data sets. So stop the misleading variance talk. That's my manifesto. And I think we're at the end. Thank you for your attention, particularly all the people who tolerated me twice here. Maybe at some point, in the not anytime soon, I could talk about my actual day job of actual cognitive neuroscience, brain imaging.